Hello, ladies and gentlemen. The title of my presentation is Design of Low Complexity Euro v3 based Deep Learning Networks with Joint Iris and Scalera Messages for Biometric Recognition Application. This paper has 3 authors. The speaker is Zipeng Fan. All of the authors are from Department of Electrical Engineering, National Zhongxin University, Taiwan. Outlines. I will give an introduction and review previous design. Then I will describe the proposed Euro v3 based deep learning method. Then I will show some experimental result and comparison. Finally, the conclusions are given. Introduction. Biometrics have been utilized to the person recognition effectively, and the iris and the sclera recognitions are the use for biometric identity identification technologies. Figure 1 shows the diagram of the preocular and the eye regions. By the iris and the sclera identification, the biometric information can be connected to the passport databases, and the personal identity will be checked. In this slide, Figure 2 shows the traditional iris or sclera image-based biometric authentications. We can see that by using the traditional method, the input eye image required to do the pre-processing. For sclera segmentation or iris segmentation, after the pre-processing process is finished, then the features extraction and the features matching can be done. Motivations. In this paper, to increase the anti-counterfeiting ability without using the additional sclera segmentations, the Euro v3 based deep learning design is developed for the joint iris and sclera based identity identifications. Next, I will describe the details of the proposed Euro v3 based deep learning method. Proposed design. These slides show the original architecture of Euro. The detection network has 24 convolutional layers, followed by 2 fully connected layers. Alternating one-by-one convolutional layers reduce the features space from preceding layers. It pretends the convolutional layers on the ImageNet classification task at half the resolution, and then double the resolution for detection. In this slide, Figure 3 depicts the architecture of the original Euro v3 tiny model. We can see that the size of the Euro v3 tiny input image is 416 by 416 pixels, and the size of the feature map output after 5 maxima pooling layers is 13 by 13 pixels. For the training and the testing processes, the visible light eye images are selected from the various databases. Figure 4 shows the applied eye image dataset for training and testing the Euro v3 based model. Then, by rotating images and shifting images for augmentations. The number of image for training and testing will be numerously increased. Figure 5 also illustrates the data augmentation of the IEEE dataset. In this slide, Figure 6 shows the labeled results of images by the labeling tool. To make the prediction of the deep learning networks model have better generalization, the image dataset is generally divided into 3 subsets, which are namely the training set, the validation set, and the test set. This study used the location procedure to distribute the dataset, where the location is 80%, 10%, and 30% respectively. Besides, the training set, validation set, and the test set are randomly divided. In this slide, Figure 7 shows the training and the testing flow to obtain the EuroV3 inference model for identity identifications. At the second stage, to obtain a fine inference model, the EuroV3 network will be trained and tested. The used procedures have 3 steps, which involve: the first step is the preprocessing for data augmentation and labeling, and the second step is the training process for obtaining the inference model, and the third step is the testing process for verify the function of the inference model. Next, I will show some experimental results and a comparison. Experimental results. For the training and the testing processes, the images are selected from the UBIRIS database. In the image dataset, 20 persons are included, and each person has 500 sub-images by data augmentation. Thus, a total of 10,000 images are utilized with a resolution of 800 by 600 pixels. To train and test the proposed deep learning-based design, a personal computer, which includes a NVIDIA GTX GPU and a CPU by the 3.7 GHz operational frequency, is applied for the evaluation platform. Figure 8 illustrates the inference results by the applied EuroV3 based model. After considering the accuracy, average IOU, and the size of the network model, when the number of used anchor boxes is reduced from 5 to 1, the mean average precision performance still keeps the same value. By trade-off the complexity and the recognition performance, the EuroV3 tiny network is used as a base model for subsequent low complexity designs. Table 1 shows the performance comparisons among Euro-based models for ocular biometrics authentications. In this table, we can see that the EuroV3 tiny model can provide the cost-effective performance for biometric authentications. In this study, in the V3 Tiny R1 model, it reduced the filter size by half. Similarly, the V3 Tiny R2 model reduced the filter size by 1/4. Although the matching rate of average IOU is decreased, it still maintains the same MAP performance in comparison with the original Euro V3 Tiny model. Next, the number of convolutional layers is reduced to decrease the computational complexity further. Compared with the original Euro V3 Tiny model, the seventh convolution layer in the V3 Tiny R3 model was deleted. For the V3 Tiny R4 model, in addition to the deletion of the seventh convolution layer, the ninth convolution layer is also removed. By experiments, the reduction does not reduce the MAP value in the V3 Tiny R4 model, but the average IOU value of the model will drop slightly, where the matching rate by the average IOU is still over 80% for the authentication application. In this slide, Figure 9 illustrates the original architecture of the Euro V3 Tiny model, and Figure 10 shows the architecture of the low complexity Euro V3 Tiny based, that is called V3 Tiny R4 model. We can see that in Figure 9, we removed some layers and reduced the number of filters in several layers. Then we obtain the low complexity Euro V3 Tiny model, just as shown in the Figure 10. In this slide, Table 2 reveals the performance comparison among 5 Euro V3 Tiny-based inference models with different low complexity architectures. In Table 2, B-flops used in Euro models means billing float operations for convolutional computations. Compared with the original Euro V3 Tiny model with one anchor, the proposed low complexity design, that is V3 Tiny R4 model, reduced the computational complexity to 15% and also keeps the same MAP value, and then holds enough average IOU performance simultaneously. In this slide, Table 3 lists the comparisons among 3 ocular biometric authentication designs. In the table, we can see that the proposed design does not need any sclera and iris segmentation, and the proposed design uses both sclera and iris information, and the proposed design can provide the identity accuracy up to 99.92%. Conclusions: the low complexity Euro V3 Tiny based biometric authentication design with joint iris sclera information is studied in this paper. By applying both iris and sclera region partially, the proposed design does not need the pre-processing process for sclera and iris segmentation. Then, by using the ubiquitous image database for evaluations, the proposed low-complexity identity classifier performs the MAP value up to 99.92% by only one anchor box. Compared with the previous biometric designs with iris or sclera information, the proposed low-complexity deep learning-based design performs higher recognition accuracy and does not need the pre-process for segmentation. These slides show the main references. Thanks for your attention.